In this video, we are going to be looking at the reduction of carbonyl compounds. Now, we've looked at the oxidation of them, so we're now going to look at the opposite reaction that we can do where we do their reduction. So let's just have a think about the oxidation reactions that we've done. So we've gone from a primary alcohol to the corresponding aldehyde. So that is the oxidation reaction occurring there. If we now do the reverse of that, so going back from the aldehyde to the primary alcohol, which is what we're doing in this video, that is the reduction reaction of that. Same thing can happen with our secondary alcohols. If we do the oxidation of that, that forms the corresponding ketone. And what we're going to look at today is the reverse reaction. So we're going to be doing the reduction reaction. So going from a ketone to a secondary alcohol. Okay. So when we've been doing the oxidation reactions, we have to use an oxidizing agent. So that means for this now we have to use a reducing agent. So for our reducing agent, the notation that we use, so for oxidizing agents, we use an O in square brackets. This one we're going to use a H in square brackets. When we do the oxidation, we're technically adding oxygens to the compound. We think of it, but we're thinking we're adding oxygen to the compound, and for a reduction reaction, technically we're adding hydrogens to the compound. So that's one way of looking at it. The reducing agent that we use is NaBH4. Okay, that's known as sodium borohydride. If you want the full name for it, it is sodium sodium tetrahydrido borate, like that. Okay. Obviously it's a lot easier just to memorize NaBH4. That's what you need to write in the exam. It has to be an aqueous solution, and we'll look at why it has to be an aqueous solution when we look onto the mechanism for this. Okay, so sodium borohydride is our reducing agent. Let's now have a look at a reaction. Let's have a look at aldehyde undergoing a reduction reaction, and the aldehyde I'm going to choose, just go for the simplest one. So ethanol, like so. Have H in square brackets to represent our reducing agent, which is aqueous sodium borohydride. So this is going to form the corresponding primary alcohol that makes ethanol. So ethanol is made from ethanol, and therefore we'll be going to making ethanol in this reaction here. Okay, so that's our primary alcohol. So aldehyde is converted into the corresponding primary alcohol, like so. Okay, also just make sure that the equation is balanced, because at the moment it's not. Over here we've got 5 hydrogens, whereas over here we've got 6, and therefore make sure you have 2 lots of the reducing agent present here. Okay, so aldehydes can be converted into their corresponding primary alcohol through a reduction reaction. Similarly, we can have a ketone. So I'm just going to go for propanone. Like that. And again, our reducing agent, sodium borohydride. So this is propanone over here. This is a ketone. When we reduce it, we make the corresponding secondary alcohol. So in this case, the corresponding secondary alcohol, so just make sure that the oxygen is still attached to the second carbon as it is over here. So this one over here is propan 2-ol, like that. Okay, and again, just double check it's balanced. We've got 7 hydrogens here, we've got 8 over here, so therefore we need 2 lots of the reducing agent like that. Okay, So ketones can be reduced back to their corresponding secondary alcohol, like that. Okay. Right. We now also need to have a look at the mechanism for this reduction. So we need to understand how this reaction works and what this mechanism is called. Okay, so we know the reduction reactions, but in terms of the mechanism, how it actually occurs, we're going to have a look at that now. So I'm just going to go for a ketone. Let's just go for propanone again. Same thing, same mechanism would apply for an aldehyde, except just that carbonyl's at the end of the chain and it's going to form the primary alcohol. In this one, we're going to form the secondary alcohol. Okay. Right, so we have our sodium borohydride in the pot. Now, what you need to know about sodium borohydride is that this compound here, it's going to release hydride ions into the solution. Okay, so this is going to release hydride ions. Now, hydride ions are hydrogen atoms that have gained an electron, and therefore they're going to have 2 electrons. So they have a lone pair of electrons on them. Okay, so these are hydride ions. Okay, we don't usually see H minus. It's usually H plus, which are protons, but H minus does exist as well. It's released from our reducing agent, sodium borohydride. As you can see, because it has a lone pair of electrons and a negative charge, this here is classed as a nucleophile. And if you remember, a nucleophile is an electron pair donor. It has an electron pair. It's ready to donate that in a reaction. A nucleophile is usually going to attack something that is electron deficient. So it's usually going to have a positive charge or a delta positive. In this case, let's have a look at our compound here and see what is polar and therefore has a dipole going across it. Now, all carbonyl compounds are going to contain this C-double-O bond. Okay, this C-double-O bond is a polar bond, because if you remember, oxygen is more electronegative than carbon, and therefore the electrons in this bond are lying closer towards our oxygen. Okay, so it is, it is delta negative here and delta positive there. There's a dipole going across that bond there. Okay, so we've got our nucleophile. That nucleophile is going to attack what is delta positive. In this case, our carbon is delta positive, it's electron deficient. So our curly arrow is going to show the movement of electrons from our nucleophile going to our carbon delta positive. Okay. So let's have a look at that occurring. I'm just going to rub this out and have it as that. So curly arrow going from our hydride ion, from the lone pair of electrons to our carbon delta positive, and that's now going to form a bond between the carbon and hydrogen. Okay, and because we formed a bond between the carbon and hydrogen, that would mean our carbon has 5 bonds, which can never happen. So that means we have to break a bond. We're going to break our pi bond between our carbon and our oxygen, and because oxygen is delta negative, that is going to take the electrons. The electrons are lying closer there to there anyways, so it's going to take the electrons in one of those bonds. If we now draw the product of that step, we formed a bond between the carbon and the hydrogen. We've still got our methyls there, so they haven't changed, but we've now got one bond between the carbon and the oxygen. The oxygen now has a negative charge and a lone pair of electrons on there. Okay. Now, this is where it was important to have aqueous sodium borohydride, because as you can see, we haven't got our final product just yet. Okay, we've got a negative charge on the oxygen. We haven't formed our secondary alcohol. If we have water present, our water is also a polar molecule and therefore has dipoles in it. So let's just pop the dipoles in like so. We've got a negatively charged oxygen with a lone pair of electrons. We've got a hydrogen that has a delta positive charge. So our curly arrow is going to go from our lone pair of electrons to our hydrogen delta positive. That's going to form a bond between the oxygen and the hydrogen, and therefore we have to, hydrogen can only have one bond, so therefore we have to break this hydrogen oxygen bond here, and that is going to occur there. So the oxygen is going to take the electrons in that bond there. Okay, and let's draw the product of this step. So carbon hydrogen bond there, methyl still there. We now have a protonated oxygen there. The bond formed between the oxygen and the hydrogen, got the OH minus there, like so. Okay, and over here, as you can see, we have formed our secondary alcohol. Okay, and that is the mechanism for this reaction. If we now have a look at the overall reaction, so I'm just going to run this out. So also this mechanism applies to aldehydes as well. So I could have easily have done that hydride ion reacting with an aldehyde to form the primary alcohol. If we now have a look at the overall reaction, okay, as you can see, we have two reactants over here and one product. Okay, if you have two reactants going to one product, that tells you that you have an addition reaction occurring. Okay, so given that there's a nucleophile at the beginning and that overall this is an addition reaction, the overall mechanism is called nucleophilic addition. So this is the name of the mechanism that our aldehydes and ketones undergo when we do their reduction.